Welcome back. So we're looking at exercises today on electricity. The questions we have, you can see on your screen. Okay, so here are the questions we're going to be dealing with. Okay, so the first question goes: a filament in a light bulb rated at 192 watts has a resistance of 12 ohms. Calculate the potential difference at which the bulb is designed to operate. So what the question is, okay, probably you went to the market, you got a light bulb, and on the packet of the light bulb you see it's rated for 192 watts, and the resistance of this light bulb is 12 ohms. So what is the potential difference, or what is the voltage that this bulb is designed for? What voltage are you supposed to place on the two pins of the bulb, okay, to operate this bulb? That's what this question is. Okay, so we have our power to be 192 watts, our resistance to be 12 ohms, and we're asked to find the voltage. All right, so we know power is IV, and we know I stands for current and V stands for voltage. Okay, and then we know that our I here equals voltage over resistance. Okay, so if we bring that into this equation, we have voltage over resistance times voltage, which is voltage squared over resistance. All right, so if we make voltage the subject of formula here, of course we're going to have this expression where we have V equal to root P times R. All right, so simplifying this, we have the root of 192 watts times 12 ohms, which gives us 48. So let's move on to the next question. We have the heating element of a stove operates at 240 volts. How much electric energy is converted to heat if it takes 5.5 minutes to bring a hot pot of water to boil? The element draws a current of 6.25 amps. Okay, so the question here is, we have a stove, okay, rated at 240 volts. All right, we want to know how much electricity will be converted to heat if this stove boils a pot of water for 5 minutes. All right, and pulls a current of 6.25 amps. Let's see how we can find the energy. All right, so if we bring out the parameters that we're given, we see that we're given voltage at 240. We have time to be 5.5 minutes. We have current to be 6.25 amps. We're asked to find the electrical energy that is converted to heat energy. So if we find the work done in making this conversion, then we know that energy already. So we're going to be using the formula work is equal to charge times voltage, and we know charge is equal to I times T. So we have I times T times V, which is current times time times voltage. So if we bring in our parameters into the formula, we have 6.25 amps for current, and then 5.50 minutes times 60 to give us our value in seconds, then multiply by 240 volts. If we do that, we have 495,000 joules. Okay, our answer is 5 times 10 raised to the power 5. So if we change this to standard form, we're going to be getting 4.95 times 10 raised to the power 5, which is approximately 5, okay, or 495 kilojoules. So number 3, the equivalent resistance of two loads connected in parallel is 25 ohms. If the resistance of one of the loads is 75 ohms, what is the resistance of the other load? Okay, so we have two loads connected in parallel, all right, to give us 25 ohms. So we have arrow 1, we have arrow 2, all right, they are connected in parallel to give us 25 ohms. If the resistance of one of the load is 75, what is the resistance of the second? So this question is basically that we have two loads. Okay, so let's say this is the first load, and let's say this is the second load. All right, they are both connected in parallel, which means both ends are connected together. Remember that, right? Okay, so let's say this is their leads, okay, their terminals. So the question is, if the resistance of one of the load is 75 ohms, so here we can say we have 75 here. All right, 75 ohms here. What is the resistance of the other load? Okay, so we're asked to find this guy. Let's call this guy X. Okay, so of course our X in this case is R2. All right, so what do we do to find this guy? Remember our effective resistance for both of them is 25. So we know that to find the effective resistance of resistors in parallel, we use this formula: 1 over REF is equal to 1 over R1 plus 1 over R2. I'm sure we remember that. If we simplify this guy by finding the lowest common factor, all right, we're going to have the lowest common factor to be R1, R2. Okay, so if we continue to solve that, we're going to have R2 plus R1. I'm sure you know how this is gotten. Okay, so this will mean our R equivalent is, of course, you know we had it in inverse here, 1 over REF. So bringing that upwards, we'll have REF equal to, we'll do the same thing here, R1 21 all over R2 plus R1. So this is our REF. We can use this formula straight if we have two resistors in parallel and we want to find the effective resistance. We don't need to start from here. We can just, because of course time is not your friend when you're having these exams, so you could just go straight to this formula for two resistors only. You just go straight to this formula, impute your values, then you get your answer. So imputing our values here, we have REF as 25 ohms, we have R1 as 75 ohms, R2 is unknown, so we have R2 here unknown, 75 ohms here too for R1. If we simplify this further, we have 25 R2. Of course, this will multiply everything here. 25 R2 plus 75 times 25, which will give us 75 R2. We'll make R2 the subject of formula. All right, and okay, we have 75 times 25 equal to 75 R2 minus 25 R2, which will give us 50 R2 here. Okay, because 75 minus 25 is 50, then 75 times 25 is 1875. If we make R2 subject of formula, we have 1875 divided by 50, which gives us 37.5 ohms. So that's what we get for this. So the value of X is 37.5 ohms. Okay, so let's move on to number 4. Okay, so a toaster that has a power rating of 900 watts, okay, draws a current of 7.5 amps. Okay, now if 2.4 times 10 raised to power 5 joules of electrical energy is consumed while toasting some bread, calculate how much charge passed through the toaster. Okay, so let's remember we have the toaster at 900 watts, okay, and 7.5 amps rating. So the work done to convert the electrical energy to heat is 2.4 times 10 raised to power 5. Okay, that's the electrical energy that is consumed. Okay, now we're asked to find the charge that passes through the toaster during this time. All right, so we know work is charge times voltage, and voltage is P over I. So we can say work is equal to Q times P over I. All right, if we make Q the subject of formula, we have Q is equal to W times I over P. Okay, so we use that to find our charge. So we have work to be 2.4 times 10 raised to power 5, multiply that by 7.5, divide by 900 watts, and we have 2 times 10 raised to power 3 coulombs, or 2000 coulombs. So for number 5, we have, for the circuit in the diagram shown below, the potential difference of the power supply is 144 volts. So we're asked to calculate, the first thing is the equivalent resistance of the circuit, then B, the current through R1, and C, the potential difference across R3. Alright, so basically we have this circuit and they've told us that the potential difference across the power supply is 144. So we can see this is a battery here, so we can see the EMF is 144 volts, or the potential difference across it is 144 volts. Okay, so first of all we are asked to find the equivalent resistance of the circuit. So we have 4 resistors here. When we say equivalent resistance, we mean what is the effective resistance. That is, if you are to replace these 4 resistors with one resistor, what is that resistor that will give you the same effect of these 4? Do you get? That's one resistor that will give you the same effect these 4 are given in this circuit. That's the effective resistance. Did you understand? So we're asked to find that. So how do we do that? How do we resolve these 4 resistors into one? Now, if we look at what we did in class, we said resistors in series have one end join together, while resistors in parallel have two ends joined together. So if you look at this resistor, okay, let's start with arrow 1 and arrow 2. If you look at arrow 1 and arrow 2 together, are they in series or parallel? Okay, so let's check. Do they have just one end connected? Yeah, they have one end connected here. Do they have both ends connected together? No, they have just this end connected. This end is not connected to this resistor in any way. Okay, so it's connected to this junction where you have the switch and you have resistor arrow 3. So it's not connected to arrow 2 in any way. On this other side, arrow 2 is not connected to it too. Arrow 2 is connected to the negative of the battery and arrow 4. So these two resistors are in series because they have only one end connected to themselves. Over to this side, arrow 3, arrow 4, okay, is the same thing. Arrow 3 is connected to arrow 4 only by one end. So these two are in series to themselves. So let's look at this whole network as against this whole network. Are they in series or parallel to themselves? Let's assume this is one resistor and this is one resistor. Are they in series or parallel? Okay, we can see that these are the two ends of the resistor, this end and this end, while these two resistors have this end and this end. If we look at them carefully, we'll see that both ends are connected to each other. This end is connected to this end of this resistor, while this end is connected to this end of the resistor. So we have two ends joined together to both resistors. Therefore, this network is in parallel with this network. Okay, let's go ahead to solve this now. Okay, so A asks for the equivalent resistance of the circuit. So for the resistors in series, let's deal with arrow 1 and arrow 2, then arrow 3 and arrow 4. So arrow effective for A, so that's why we have arrow EFFA here. Arrow effective of A is arrow 1 plus arrow 2. That's how we calculate resistors in series. So we have 26 plus 38, which gives us 64. Then arrow effective for B, we have arrow 3 plus arrow 4, which gives us 61 ohms plus 35 ohms, and gives us 96 ohms. Alright, so let's find arrow effective. Now, arrow effective is now that effective resistance of all of them combined. We've reduced this to one resistor and this to one resistor, so we have just two resistors now, and we're trying to find their effective resistance. Okay, so remember what I talked about previously with the formula, okay, where we had 1 over arrow EFF equal to 1 over arrow 1 plus 1 over arrow 2, and I said we could use arrow EFF equal to arrow 1 arrow 2 all over arrow 1 plus arrow 2, okay, to solve our questions. Instead of going through the long length, you can just do this straight. So we're doing that here now. So we have arrow EFF equal to arrow effective A times arrow effective B all over arrow effective B plus arrow effective A. So this gives us 64 times 96 divided by 96 plus 64. Okay, so we get 6144 divided by 160 ohms. Okay, and this would give us 38.4 ohms as the equivalent resistance of this, okay, this network of resistors. So next we're asked to find the current through arrow 1. Okay, so if we need to find the current through arrow 1, we have to understand how current flows in a circuit. Remember I said in class that current flows through the path of least resistance. Okay, so obviously once it starts flowing here, it comes and it is resisted on this part and on this part. Okay, but the equivalent resistance of this network is smaller than the equivalent resistance of this network. So we have 64 ohms here in total, and we have 96 ohms here in total. So it means the current is going to flow more through this side than it will through this side. We're going to have more currents flowing here where it's least resisted. Also, the voltage across this terminal and the voltage across this terminal will be forced to be the same. You need to note that, because this node is the same with this node. This node is the same with this node. The voltage here cannot be different from the voltage here. Okay, this is more like, just consider this like a wire. This whole line has 1 voltage. This whole line has 1 voltage. Okay, so the voltage across this network of R1, R2 is the same as the voltage across R3, R4. But the voltage across R1 and in between here, R1 and R2, is different from the voltage across here and here. The same thing happens here. The voltage here, between here and here, is different from the voltage between here and here. Okay, because their resistances are different. Okay, so we are asked to find the current through R1. Now, I initially mentioned that the current flowing through this path will be greater than the current flowing through this path because the resistance here is, the resistance it experiences is lesser than the one here. Now, when the current comes here, the current doesn't see the effect of this resistor. It doesn't just feel the effect of this resistor at this point. All right, it's more like you have two guys who are blocking a space and someone wants to pass through them. Okay, you're not passing through them based on the strength of one man. You're passing through them based on the strength of both men together. All right, so this current is going to feel the resistance of both these resistors together and not just one resistor. So when you're calculating anything that has to do with current going through one resistor like this, you have to note that the flow of your current is based on both resistors. So it means that the current flow through this resistor is exactly the same current flow through this resistor. Okay, because it is the same amount of current that will flow through this path like this. The same amount of current will flow through this path like this. So the same current that flows through R3 is the same current that flows through R4. So what we can do to find the current flowing through R1 is to find the current flowing through this network. Okay, so to get the current flowing through this network, we need to know the voltage across this point. Okay, because of course current is equal to V over R, right? So we need voltage over resistance. So we need to know the voltage across this point. Okay, then we divide it by the resistance, okay, across the same point. Then that will give us the current flowing through that path. So if we do that, we're going to have our voltage as 144. Remember, the voltage across this place is 144 because that's actually the voltage across the node of the battery. Okay, the terminals of the battery. So we have this to be the positive terminal. That's if this switch is closed. Okay, we have this to be the positive terminal and we have this to be negative terminal, and the battery voltage is 144. So we're going to experience 144 across this terminal. So we divide 144 by the resistance of both these resistors. Okay, so if we do that, we're going to have 2.25 amps. Now that is the current that flows through R1 is the same current that flows through R2. Okay, so C says we should find the potential difference across R3. Like I said, the potential difference across this network is 144 volts. The potential difference across this network is 144 volts. So we can find the voltage across this guy alone by first of all finding the current that flows through this network. Okay, just the way we did with this network, we will find that current that flows through this network. Okay, after we've done that, we're not going to use that current because that's the current that flows through R3. We'll use that current in combination with the resistance to find voltage across this resistor. Now, this is what we're going to do. We're going to do the same thing we did here to find the current. So we're taking the voltage across this network, dividing it by the resistance felt across the same network. So that will be the effective resistance of B. So remember that what we did was take this network, this whole network as A. That's this whole network here. We took it as our A, and we took this whole network as our B, this one here. Okay, when we divide that, we have 144 divided by 96, which is the effective resistance of this network here. So if we divide that, we have 1.5 amps. Okay, so we can see that it's evident that the current that flows through this path is more than the current that flows through this path, which actually means that current flows through the path where it's least resisted. Okay, so we have 2.25 amps flowing through this network, and we have 1.5 amps flowing through this network. All right, so we have 1.5 amps here flowing through that network. So we can easily find the voltage across R3 by using that current that flows through it, okay, and multiplying it by its resistance, because we have V equal to IR. So if we multiply that current by this resistance, because that is the current that flows through this resistor, when we multiply that current by this resistor itself, we will find the voltage across this resistor alone. Okay, so if we do that, we have 1.5 amps times 61 ohms, and that will give us 91.5 volts. Okay, so let's move on to number 6. A 9-volt battery is supplying power to 3 light bulbs connected in parallel to each other. So the resistances R1, R2, and R3 of the bulbs are 13.5 ohms, 9 ohms, and 6.75 ohms respectively. Find the current through each load and the equivalent resistance of the circuit. The question is making us understand we have 3 bulbs which are loads. So I would represent them with the symbol for load or resistance, okay, instead of the bulb. We have 3 of them connected in parallel. Okay, we have them in this kind of way. These are their leads, and we have R1 to be 13.5, 13.5, and we have R2 to be 9 ohms, and we have R3 to be 6.75. all right, and we're asked to find the current through each load and the equivalent resistance of the circuit. So we are finding the current through R1, the current through R2, and the current through R3. Let's not forget we have 9 volts across this. Okay, so we have 9 volts across this. So we have this, okay, 9 volts. The first question says we should find the current through each load. Okay, so current flows this way, gets to this junction, and has to split in 3 ways. So we're asked to find how this current splits. How does it go through this, and through this? Remember, current flows through path of least resistance. So we expect a higher current to flow through 9, okay, compared to the other 2 resistors next to 6.75. Then 12.5 should have the least flow because it poses the most resistance to the current. Okay, so that's one way to even check if your answer is correct or not when you're done solving. So our first step will be, we remember the formula for finding current. It's voltage over resistance. All right, so for R1, which is 12.5 volts, we have voltage to be 9 volts. Okay, the voltage across it is 9 volts. You can see this pin, this point of the resistor is connected to the positive of the battery. This point is connected to the negative of the battery. All these points are connected together. This is a junction, this is a junction. All these points are connected together. All of them connect down here. So the voltage, the potential difference across this point and this point is 9 volts. So that's also the same potential across the terminals of this resistor. So we have 9 volts divided by 13.5 ohms. Okay, so if we simplify or solve that, we're going to have 0.667 amps. Okay, so for R2 we have the same voltage but a different resistance. So 9 divided by 9 ohms, we have 1 amp. So for R3 we have 1 divided by we have 9 volts divided by 6.75, which gives us 1.33 amps. So we can see that the highest flow of resistance goes to the 6.75 resistor. Okay, so the next is the 9 ohm resistor, and the next is the 13.5 ohms resistor, because the 6.5 ohms resistor is the least resistance that we have here. So it allows more current to flow, which is 1.3. Then 9 is the next least resistance we have, which allows 1 amp to pass through it. And then this one should be the least, which allows 0.667 to pass through it. So having gotten that, we're asked to find the equivalent resistance of the circuit. Alright, so to do that, we remember our formula: 1 over RE effective equal to 1 over R1 plus 1 over R2 plus 1 over R3. If we simplify that, we're going to have these. So whenever we have 3 resistors in parallel, we can use this formula straight. We're going to have 9 ohm times 9.75, that's R2 times R3, then plus R1 times R3, which is 13.5 times 6.75, times R2 times R1, okay, which is 9 times 13.5 divided by R1, R2, R3. So if we simplify that, we're going to have 1 over R effective to be, okay, this, okay, if we use a calculator, simplify further, we have 0.366 as 1 over R effective. Don't make the mistake to think this is your effective resistance. No, we have to still find the inverse of this to get our effective resistance. So REF is equal to 1 over 0.366 ohms, which then gives us 2.73 ohms. Okay, but then whenever we have 3 resistors in parallel, we can go straight to use this formula, which is the inverse of this. Okay, all right, so we can just go straight to put in the values and we're going to get our answer. For number 7, we have for the circuit shown in the diagram below, the potential difference of power supply is 25 volts. Calculate the equivalent resistance of the circuit, potential difference across R3, the current through R1. Okay, so we have 25 volts here and we're asked to find the equivalent resistance of this circuit. So let's check, are these resistors in series or parallel to themselves? Okay, because solving these questions can only begin after you have been able to find the configurations of these resistors. If you can't succeed with knowing the configuration of these resistors, then you can't solve questions like this. We have resistor 1, we have 2 and 3. Let's check 1 and 2. Are they in series or parallel? Okay, so we have this point from R1 connected to this point in R2. We have this point also connected to this point. So you can see R1 and R2 are in parallel. Okay, when it comes to R1 and R3, okay, we see that one part of R1 is connected to one part of R3, the other part is not. It's connected to the battery. Okay, when it comes to R2, we see that one part is connected and the other part is not. It's connected to the battery too. So R1, R2 are in parallel with themselves, but R1 is in series with R3 and R2 is in series with R3. Okay, if we want to resolve this, it's wiser for us to solve these ones that are in parallel first, and then as we resolve this parallel network into one resistor, and that one resistor will now be in series with this one, obviously, because it will be just one end connected. Then we can now solve both of them in series. So that's what we're going to do here. Okay, so we take R1 and R2 to be our first network, which is A. That's R effective A. To find that, we use, of course, the formula I first gave for solving both 2 resistors in parallel. Okay, so have R1, R2 over R2 plus R1. If we bring in the values, we're going to get 375 ohms over 40 ohms, and that will give us 9.37 amps. So what this means is the effective resistance we have here, okay, which is just one resistor, one big resistor down here, that effective resistance that will replace these other 2 resistors here in this network is 9.37 ohms. So basically we have reduced our circuit to something like this. Okay, yeah, I didn't mention in class, but this is also the symbol for resistors. So we have this symbol, we can represent resistors like this, or we can represent resistors like this. So don't get confused when you see this, referred to as a resistor. Okay, so this is RU3 as we have it, and this is our RU effective for A, right? So we have reduced this whole network, okay, of the circuit to this. So what do we do next? We find RU effective, okay, for these 2 networks. So that will be RU effective A plus RU3, which will give us 9.37 ohm plus 6 ohms as the effective resistance, which is 15.37, which is approximately 15.4 ohms. So the second question is to find the potential difference across R3. To find voltage across this point, we use our formula, which is V equal to IR. But in that formula now, we have only one variable given, which is arrow. We don't know the voltage across this point, and we don't know the current flowing through this point. So what do you think we do? We need to find the current flowing through arrow 3 to get the voltage across its points. Any current flowing through arrow 3 has to be the current flowing through the full circuit. Yeah, because current goes through this point, comes to this junction, splits, comes through this place, comes through this place. But here, that current combines together to pass through arrow 3. So whatever current it is that flows through this place, okay, will be the current that flows to arrow 3. Since that is known, okay, to get the current that goes to arrow 3, we have to find the current that flows through this circuit. And one way to find the current that flows through the circuit is to divide the voltage across, okay, this circuit by the resistance across the circuit. Okay, so the voltage across this circuit, of course, has been given as 25 volts, and the resistance across this circuit, of course, we have found to be 15.37. That's the effective resistance. So we're going to do that here as V all over arrow effective. So that will give us 25 divided by 15.37 ohms, and we're going to have 1.627 amps as the current that goes through the circuit, which is also the current that goes through arrow 3. So after we have found the current, we have current now that goes to arrow 3, and then we have our resistance. So we can use those two parameters to find our voltage. And if we do that, we have V is equal to I arrow, so I is 1.627 times 6. Okay, so that will give us 9.76 volts as the voltage across this resistor. So we look at the third one, which is C. We're asked to find the current through arrow 1. When you have resistors in series, the voltage across each resistor sums up to be the voltage across the circuit. In this case, we have here, where we have arrow effective A and arrow 3 as resistors in this circuit, and both of them are in series. Okay, if we want to find the voltage, the total voltage in this circuit, one way we can do it is by finding the voltage across arrow EFA, finding the voltage across arrow 3 and adding both of them together. That way we'll have the voltage across the terminal of this circuit. Okay, so when I say voltage across the terminal of the circuit, remember that we have this circuit separately like this. This is a terminal for the circuit, and then this is a terminal for the circuit, and then we have a battery. Okay, a battery somewhere else. Okay, this is the terminal for the battery, this is the terminal for the battery. So we now bring this battery to this circuit and join them together to have this. Okay, so the voltage across this terminal, okay, is now the voltage that this battery would come with. So the voltage across this circuit now is V, the voltage across arrow EFA, that's arrow effective A, okay, which is this resistor, okay, plus V arrow 3, that's the voltage across arrow 3. So if we sum up both voltages, these two voltages, will have the voltage across the battery, or the EMF of this battery, because the voltage across this battery will split between these two resistors. Okay, so we'll have a voltage drop here, and we'll have a voltage drop across this one too. So if you sum both voltages together, we'll get the voltage of the battery. So if we are to find the current through arrow 1, what we can do is, since we have this formula here, we can subtract arrow 3, the voltage across arrow 3, which we have found, from the battery voltage. That's what I'm trying to say. Okay, if we do that, we automatically get the voltage across this network. Okay, that's this place, arrow AFFA. But then the voltage across arrow 1 is the same voltage across arrow 2, because their nodes are joined. Okay, if you have 5 volts, let's say you have 5 volts at this point and 0 volts at this point, that's this point here, this junction here, this node here will experience 5 volts, and this node here will experience 5 volts because they are joined together. Do you understand? So we have this whole network in series with this one. So the voltage across here plus the voltage across this resistor will give us total voltage of the battery. So armed with that knowledge, we come down to solve for the current through R1. So the current through R1 is V over R1. Okay, where our V, that's the voltage across R1, is the voltage of this battery, which is 25, minus the voltage across R3. So we'll have V minus V3 all over R1. So if we do that, we're going to have 25 volts minus 9.76 that we got here, divided by 15, which is the value of R1. So if we do that, we're going to get 1.02 amps as the current through R1. Okay, so let's go to number 8. We have a battery sends a 2.25 amps current through a circuit for 1.5 minutes. If a total of 8.10 times 10 raised to power 2 joules of work was done by the current, what was the potential difference of the battery? Okay, so we have these parameters: current 2.25 amps. Okay, the battery sends 2.25 amps current. Okay, we have it sending this through a circuit for 1.5 minutes. So time is 1.5 minutes. Work done is 8.10 times 10 raised to power 2. So we're trying to find V. So we have work to be QV, and Q is ITV. I'm sure we remember that. So if we make V the subject of formula, we have W all over IT. If we put in the values of our parameters here, we have that everything will resolve to 4 volts once we solve this with the calculator. Okay, so we have IT to be 2.5 times 1.5 times 60. 1.5 is multiplied by 60 to give us our answer in seconds instead of minutes. So we simplify this to get 4 volts. Let's look at number 9. The heating element of an electric kettle draws 7.5 amps when connected to a 120 volt power. Okay, what is the resistance of the element? Okay, this heating element draws 7.5 amps whenever you connect it to 120 volts. So we are asked to find the resistance of this element, because it's the resistance it has that allows it to draw 7.5 amps. So we have current to be 7.5, voltage to be 120. So resistance will give us V all over 1. That's voltage over current. So voltage is 120, current is 7.5. If we simplify that, we have 16 ohms. So we have 16 ohms for the resistance of the element. Number 10. An electric kettle which operates on a 120 volt supply has a heating element with a resistance of 10 ohms. Okay? If it takes 3.2 minutes to boil a liter of water and the energy charge is 6.5 cents per kilowatt hour, calculate the power rating of the kettle. 1. 2. Calculate the cost to boil the water. So we have these parameters. We have voltage to be 120 volts, resistance to be 10 ohms, time to be 3.2 minutes, cost to be 6.5 cents per kilowatt hour. To solve for A, alright, we remember that we have power to be equal to V squared over R. You know, power is IV. I is equal to V over R. So if we replace I with V over R, we have V squared over R. So to get the power rating of this kettle, we bring in the parameters 120 squared all over 10 ohms, which will give us 1,440 watts. So B, we're asked to find the cost of boiling the water. Okay, so kilowatt consumed. We need to find what kilowatt was consumed. So to find that, it means we're multiplying the kilowatts we got, okay, multiplying it by the number of hours that we used the equipment. So we have that to be 1,440 watts divided by 1,000, so that this can be converted to kilowatts. Okay, we're dividing it by 1,000 so it can be converted to kilowatts. Then we have 3.2 minutes, okay, divided by 60, so we can convert this to seconds. All right, so if we simplify that, we have 0.0768 kilowatt hour. So now that we have that, we now use that to find the cost. So this tells us that this thing costs 6.5 cents per kilowatt hour, and we don't even have up to 1 kilowatt hour. We have 0.0768 kilowatt hour. So we multiply 6.5 cents by 0.0768 kilowatt hour, we're going to have 0.499 cents, which is 0.5 cents. So let's look at the 11th question. A load R1 is connected in series with two loads, R2 and R3, which are connected in parallel with each other. If the potential difference of the power supply is 180 volts, find the current through and the potential difference across each of the loads. The loads have resistances of 25, 30, and 6 ohms respectively. Just like what we had before in the previous question we did, we have so let's say we have this load connected like this. Okay, pardon, this is my drawing. Okay, so we have these two loads in parallel and we have this in series with them. Okay, I'm sure that's easy to understand. And this is load R1 and this is load R2 and this is load R3. Okay, and load R1 is 25, load R2 is 30, load R3 is 6. Okay, we have to find the current through them and the potential difference across each of them. Okay, so I'm finding current through R1, R2, R3, and potential difference across R1, R2, R3. So the first thing we need to do, if we need to find the current through them, is to find the current through this circuit. Okay, if we find the current through this circuit, obviously we have found the current through R1, because any current flowing through the circuit is that same current that's flowing through R1 because of how it's positioned. It's just that it will split between R2 and R3, but the network R2, R3 together will experience that same flow of current. Okay, so let's find that. So we have for the resistances in parallel, which is R2, R3. Okay, we can use this formula to solve them like was said earlier in class. So if we do that, we have 30 ohms times 6 all over 6 plus 30 ohms, which will give us 5 ohms. So we have 5 ohms here as effective resistance. So we can remove these two resistors and put just one resistor here. Okay, which is 5 ohms, and we'll have exactly the same effect, okay, in this circuit as if we have these two here. So if we remove these two and put in 5 ohms here, all right, it will just be same thing. Okay, so having done that, we will now go to find the effective resistance, all right, in the circuit by adding R1 to the 5 ohms we got. Okay, and after we've done that, we can now use that value, okay, we can use the value of the effective resistance to get the amount of current flowing through the circuit with the voltage across, using the voltage across the circuit, which is the voltage of the battery. All right, so let's move on. So to do that, okay, we have 25 plus 5 ohms, which is 30 ohms. That's the effective resistance now of the circuit. So 25 ohms sums up with 5 ohms to give us 30 ohms, where 25 ohms is the resistance for R1 and 5 ohms is the effective resistance we got for R3 and R2. All right, so therefore the current through R1 is current through the circuit. So which means if we find V over R1, which is the voltage across the battery divided by the effective resistance of the full network of resistors, okay, we have 6 amps, which happens to be current through the circuit, but at the same time the current through I1. So our current through I1 we have gotten as 6 amps. So we need to find the voltage for the parallel network. So the voltage for the parallel network is going to be 180 volts minus the voltage across R1. So 180 volts being the voltage of the battery minus the voltage across R1, okay, will give us 6 amps times 25. Voltage across R1 is IR. Remember that V is equal to IR. So we take I to be 6 amps for R1, which is what it is, then multiply it by the resistance of R1, which is 25 ohms. So if we do that, we have the voltage across R1. So if we subtract that voltage from 180, which is the voltage of the battery, we have that 30 volts is what we have on the network of R2 and R3. Okay, so let's get that drawn here again. we have this battery, okay, and we connect it to arrow 1, and arrow 1 connects to these resistors in parallel. Okay, so what I'm saying is the resistance, the voltage, sorry, across this network, okay, plus the voltage across this network will sum up to give us the voltage across this battery. All right, so that's what we did here now. So if we subtract the voltage across this resistor from the voltage across this battery, we're going to get this voltage. Okay, so this 30 volts now is the voltage across this network. Okay, so having gotten the voltage across this network, we can now use their individual resistances to get the current flowing through each of them, because the voltage across this network is the same as the voltage across each of these resistors, since they are both connected at both ends to those nodes. Okay, so current through arrow 2 will be V over R, which is the voltage across the network divided by the resistance, which is 30 ohms, so that will give us 1 amp. Then current through I3 will be same thing, V over R, 30 volts, which is voltage across the network divided by its resistance, which is 6 amps, and that will give us 6 ohms, and that will give us 5 amps. So voltage across R1, which we have found here, which is 6 times 25, will be 150 volts. Voltage across R2, which is 1 amp times 30 ohms. Okay, 1 amp times 30 ohms. Remember, 1 amp came from this solution where we found the current going through I2. So we multiply that I2 current by its resistance, which is 30 ohms, to get the voltage across it, which is 30 volts. Okay, we have already found this. I'm just still showing you how else we could do that. So you can see that we have 30 volts here, and here we also had 30 volts when we subtracted the voltage here from this to get the voltage across this. So even if we decide to solve like this, we'll still get the same answer. Okay, so voltage across R3 is 5 amps, which we got here, divided by its resistance, which is 6 ohms. If you multiply that, you have 30 volts. So you can see of a truth that the voltage across this guy is same voltage across this guy, because they are both connected to the same nodes. Okay, all right, so that's the much you can take today for exercises. Thank you for joining us, and I hope to see you when we're solving questions from past exams. Thank you.